Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and we're going to talk about a continuation of what we talked about last time, where we introduced the concept of time stepping and for the numerical approximation of initial value problems. So we essentially encapsulated many different techniques into one comprehensive set that we call the prediction correction methods, which are essentially the same but different levels of approximation, different orders of approximation, or inherently basically different levels of truncation of the Taylor series that approximates the derivatives. So that led to methods that have different levels of complexity, and with added complexity you have different higher order of approximation. So the method tends to converge faster with smaller values of the time step. Now, I mentioned too that there's a trade-off between the order of approximation and how small you can make the delta t. There's issues with resolution in the computer. There's issues with tolerance in the computer, and there's issues with the internal or inherent machine precision of the computer where you're programming this, and essentially the architecture of the microprocessor in which you're programming. Normally, you would adopt a double precision standard for encoding floating point numbers. Floating point real numbers, essentially a format that entails the double precision in particular is an 8-byte representation or 64-bit representation of a real number that allows you to actually have a higher definition than single precision. Obviously, higher definition of the number of significant figures that you can have in the decimal location, the fractional location of the number. Now, if you increase the order of approximation of the method to, say, a fourth order approximation like RungeKutta, you essentially are adding complexity to the algorithm, because you're calculating a prediction of the solution at the next time level and then 3 corrections of that solution to come up with a final approximation at the next time level. And then you have to do it again over and over to as many number of time steps that you predefine you are interested in the solution. But that also means that you can afford to have a smaller, an actual larger time step. You can afford to have a coarser time step size, which means that you possibly and feasibly can stay within the precision of the computer, even for complex problems, even for problems that you anticipate can have some kind of strange behavior, like maybe near singular behavior or something like that. Let's say that you're trying to solve a differential equation where the expected solution, where the differential equation happens to be nonlinear, for example, or the equation itself has some singular points at some locations, or the expected solution is expected to behave weirdly, also perhaps singular or otherwise. Now, in that case, when the computer detects an anomaly like that, the computer doesn't know how to act. And if you tell the computer, well, you're going to use the size of the time step, and you're going to interpolate the solution in between those 2 points, and then you're going to calculate an implicit integral in between these 2 points to integrate the solution over time, the computer is more than likely going to make a mistake if there's some sort of singularity or near singularity in the middle. Even if it's a near singularity, it doesn't have to be a full singularity. Even if it's a near singularity, something like an asymptote that tends to infinity, but it gets closer to that, a very large slope or something like that, that defies the machine precision. Remember that the computer has a prescribed precision, depending again on the level of precision that you're using for representation of your real numbers. But even if you're close to a singularity, then the solution, the computer is going to complain about it. So there are ways to kind of avoid this, automatic ways that you don't have to worry about. And those methods or methodologies or schemes basically entail trying to sort of anticipate what the solution is going to do at the next time level and decide what you're going to do next. The technique that we're going to learn today has to do with, instead of using a fixed time step, you're going to let the computer, or through an algorithm, you're going to try to figure out whether the computer is going to be within some, or the approximation is going to be within some tolerance. And if it's not going to be within the tolerance that you prescribe, then you are going to tell the algorithm, well, break that time step into pieces. We cannot afford that large time step because the solution that we're going to get is not as good as as the one we want. There are other schemes out there that do this in many different manners. There's the most common ones use different order approximation. Like, for example, imagine you can use the modified Euler, which is second order in time approximation, and then you can use a RungeKutta, which is a fourth order in time approximation. Since you know the order of approximation between the two, you can sort of predict what the error, if you use both methods simultaneously and the same time step size, you can sort of predict, given the solution at the next time level provided by both methodologies, you can sort of say, well, the difference between these two gives me some indication of the error, the numerical error induced by the algorithms. And using that error, then you can actually establish with a tolerance that your delta t has to be either even a little smaller or a little larger. So you can do adaptive time stepping based on different orders of approximation, and then use that information to decipher what's the size of your time step. What we're going to learn today in terms of adaptive time stepping or modified time stepping is use the same order of approximation. In particular, we're going to use RungeKutta because, as I said, it's the most commonly used of all numerical integrators for first order differential equations. So we're going to use a RungeKutta, which is order 4, delta t to the power 4, accurate. And then what we're going to do is we're going to break up the time step in half, right? So we know that if we approximate the solution to the next time level in one time step, we're going to get an answer. And then if we actually take that time step and break it in two and redo the approximation at the next time level using these two half time steps, the solution that we are going to get is going to be slightly better than the other one. And we know that it's going to be slightly better by a factor of 2 to the power of 16. Because, 2 to the power of 4. Because we know that the error in the approximation is in the order of delta t to the power of 4. And we know we use a time step size that is half of what we used before. So we take that 2, which is the size of the delta t that you broke, take it to the power of 4, which is the order of the approximation, and we have an order of 16 of improvement in the error between the two solutions that you approximate. And then you use that information to go in reverse, to just reverse engineer a delta t that you would need to satisfy some prescribed tolerance. So this is in a nutshell what this adaptive technique will do. And this in particular is called the Richardson extrapolation. So let's develop this idea and then put it into practice in a MathCAD spreadsheet for a solution of a first order initial value problem. So this is modeling methods in ME. And we're going to talk about adaptive time stepping. So why adaptive time stepping? Let's just summarize what I just said. There are instances in which the nature of the governing equation, let's say the differential equation that you're given in the initial value problem, for example, when a function of y and t that defines the governing equation is singular or near singular at certain values of y or t, or the function itself is highly nonlinear, the numerical approximation of the solution may require extreme, I want to say extreme in quotes, resolution of the time step size. To provide an accurate approximation. All right, so there's instances. For example, the differential equation that we worked with last class is one where the function itself had a tangent of t, and you know that the tangent of t goes singular at certain values of t. And so if you just use the algorithm that we provided blindly for functions for values of time that would actually go through the singular location, the algorithm will have something to say about that. It would actually complain, and more than likely, if you hit exactly the point of singularity, it will crash. So we need ways to avoid this, because we noticed that that particular differential equation that had a function f that looked like it was singular, it had a tangent of t, that differential equation had a solution that was non-singular. It was perfectly smooth. It had sines and cosines and so on and so forth. Okay, these extreme resolution of the time step size, which means just break it up into very, very tiny sizes or tiny steps. These unnecessarily slows down the solution process at regions where it is not necessary to have such high refinement. That is, there might be portions of the solution that require a very small time step, but there's portions of the solutions that are very smooth, where the function behaves nicely, where you can afford to have a very large time step. So this is of a premium to be able to figure this out and to actually use an effective and efficient time step so that you can get a solution in time. Now, it might sound odd that we would need to accelerate a solution that already takes a split second, because as we saw in the implementation last time, we put in a solution, even if we put 100 or 1,000 time steps, the solution takes a split second to converge. But remember, normally when we're solving these types of problems, are being solved millions of times for the purpose of maybe a control system, a controller that is already pre-programmed into a microcontroller, a microprocessor that is sending that is receiving input from some sensors in a system, and is sending the outputs to some pump or some other device that is going to perform an action. And so you have the necessity to solve these equations, which are normally not just one, but thousands, as we'll see in the next class. You have the necessity to do it as efficiently as possible, so that you can have an efficient controller, for example, that can react on time. So we're going to talk about a technique known as Richardson's extrapolation. Can be employed as a way to perform adaptive time stepping for error. Is it an R? Error control. So the idea is that we are going to try to predict when the error is going to get high, and at that point we make the delta t smaller, and then in regions when we know that the solution is well behaved and smooth, we bring the error up to, the delta t as high as possible, so that the solution is efficient, the solution process is efficient. So again, the idea here is to compute two estimates of the solution at time step n+1. So we're going to compute two estimates of the solution at the next time level. One, using a full time step, delta t, and two, using two half time steps, delta t over 2. So we're going to get to the solution estimate at the next time level, n plus 1, by doing it in a full step, delta t, and by doing it in two half steps. We should get the answer. Those two answers should be comparable because they represent an approximation of the solution at the same time level, level n plus 1. However, one should be slightly better than the other. And of course, we expect this one to be slightly better than this one because we're breaking the delta t in half. Now, the way it's going to work, we can do this with any of the predictor corrector techniques that we learned last time, but we're going to do it with RungeKutta. We're going to stick with that. So you are going to evaluate the solution at the solution what we call 1. That's the full time step solution at time step n plus 1 using yn plus 1/6 of, remember, k1, 2k2 plus 2k3 plus k4. This is the RungeKutta solution. You calculate the parameters k1 through k4 and linearly combine them this way to approximate the solution. This is a predictor and the three correctors, right? K2, K3, K4. And the second estimate of the solution, which we call yn plus 1, second estimate. Actually, we're going to calculate 1n plus a half, halfway through the time step, or through the time level. It's yn plus 1/6 k1 2 plus 2 k2 2 plus 2 k3 2 plus k4 2. This is again the linear combination of RungeKutta solution. So we have the solution at halfway to the time level using half a time step, which will give you these parameters k1 to k4. And then the next one, kn plus 1, is yn plus a half, second estimate, plus 1/6 of k1 plus 2k2 plus 2k3 plus k4. So right off the bat, we've actually increased the complexity of the algorithm because we've added a few extra steps. So before, this is the only thing we used to do, and that's it. That's a solution at the next time level, and then we we loop over all the time levels. What we're going to do now is just compute this one and this one. Now, these two solutions right here are the solutions of what the estimates of y at the next time level. Then, the error bound. So we know that these two solutions represent estimates of the solution at the same time level. However, there's an error between the two. The two approximations is error is equal to 2 to the power of n divided by 2 to the n minus 1, yn plus 1, 2, minus yn plus 1, 1. Estimate 2 minus estimate 1 times that factor, where n is the order of the approximation. So this is a general expression that you can use with whatever order approximation, but we know that for RungeKutta, the order of the approximation is n equal 4. Because RungeKutta is fourth order accurate. It's delta t to the power of 4 convergency accurate. So the error for RungeKutta 4 is equal to 2 to the power of 4, which is 16, divided by 15, yn plus 1 minus yn plus 1, 1. Now, it is important that we don't confuse this with the error of the solution, okay? Because if we knew what the error was, then we would know the exact solution. This is not the error between the numerical approximation and the exact solution. This is the expected error bound given the order of approximation of the solution between the first estimate and the second estimate. The difference between the two gives you an estimation of how much the error is actually decreasing, so it provides a bound for you to have an idea of what the error is, the order of magnitude of the error, the bound, not the actual value. So, given that information, we're going to use it in reverse now. We can use these formulation in reverse to estimate the necessary time step size DeltaT Max that would be needed to achieve a prescribed tolerance of the solution error, or the approximation error. So again, what we're going to say is that, well, we're going to replace this error with epsilon, right? I'm going to say I can only afford to have an error of 10 to the minus 3. Just give an arbitrary number. And if that's the case, then I can work this in reverse to predict what is the DeltaT Max. There's the maximum size of DeltaT that would be needed to achieve an error that is as much epsilon. So DeltaT Max will be DeltaT, the DeltaT that I use in the original estimation, 2 to the power of n minus 1 divided by 2 to the n, epsilon divided by yn plus 1, the second estimate, yn plus 1, the first estimate, to the power of 1 divided by n plus 1. So again, n is the order of approximation. So again, for RungeKutta, n is equal to 4. So the DeltaT Max that the RungeKutta estimation, RungeKutta 4, we'll call this RungeKutta 4 with capital, is equal to DeltaT 15/16 epsilon yn plus 1, second estimation, minus yn plus 1, first estimation, to the power of 1/5. Now, you can identify that this number right here, yn plus 1 times 16 over 15, is what we call the error in the RungeKutta approximation. So we can calculate that error and place it here. So the DeltaT Max, RungeKutta 4, is equal to the DeltaT that I use for these estimations, epsilon over the error of the RungeKutta 4 approximation to the power of 1/5. Okay, so now I know how to calculate the maximum DeltaT that I can afford, so to be able to satisfy this tolerance. Now, how does it work? Again, I have a prescribed DeltaT. I start with a DeltaT. And I say that DeltaT is, I don't know, 10 to the minus 1 second, so 1 centisecond, 10 to the minus 2, whatever. Okay, then you use that to calculate an estimation of the solution at the next time level, which is y1 and y2 at the next time level n plus 1. So you use that DeltaT, the prescribed DeltaT, right? with that, you calculate an error between the two. This error of RungeKutta 4, 16 over 15 of the difference between the two, which we were still in the same time level, n plus 1. Then you take your tolerance, which you prescribe arbitrarily, and say, well, the maximum error I can afford in my solution is 10 to the minus 3, something like that. Divided by that, take it to the power of 1/5 and multiply by the delta t that you use, and you get a new value of delta t. If this delta t is larger than the delta t that you use, you're okay, because you already have a good estimation of the solution that satisfies the tolerance. That means that the delta t that you use is safe. However, if the delta t, this new delta t that you calculate is smaller than the delta t, means that the delta t that you used in the first place gave you a solution that has an error that is larger than the tolerance that you prescribe. So we need to do something about it. So let's go here. Therefore, an initial course time step size delta t can be set up. So you can set up your algorithm with a course value of delta t that doesn't have to be refined, along with a prescribed tolerance epsilon to compute at every time level if adaptation is required. Again, it will be required if the delta t max is smaller than the delta t that you use. So that is it goes like this. So this is another addition to the algorithm. So you have to add a conditional, you have to add a question. That is, if delta t max of the RungeKutta 4 is greater than the delta t that you use, tolerance is already satisfied, no adaptation is required. So what you're going to do is use the approximation error that we just computed to advance the solution in time. So essentially, the solution at n plus 1, the definite solution at the next time level that you're going to use is estimate number 1, which happens to be the less accurate of the two, remember, because estimate number 2 is using 2 half-time steps, so it, in essence, is a better one. But you're going to add this error of RungeKutta 4 that you calculated, which uses the difference of yn plus 1 and yn plus 2 with a 15/16th or 16/15th factor in it. So that is your new estimate of the solution, and that's the one that you're going to use to advance to the next time level, n plus 2. So you're done. However, if delta t max is less than delta t, so when you apply this formula, you find that the delta t required to satisfy the tolerance is less than the one you use, then tolerance is not satisfied. Adaptation is required. So how are we going to adapt? So what we're going to basically do is use its delta t now. So instead of going back and repeating the entire solution with this new delta t that you just calculated, what you're going to do is subdivide the current time step into ns sublevels. You're only going to do it for these time steps, because remember, the key to this is that later on, when the solution becomes smooth, you don't have to adapt the solution. The tolerance might already be satisfied with the coarse delta t that you're already using, so you don't need to do the subdivision all the time, only when you need it. So what you're going to say is that I am going to break this up and use ns is equal to delta t divided by delta t max of RungeKutta 4. This is a RungeKutta 4, which doesn't have to be. You can do this entire formulation for any other level of approximation. So this is the number of time levels that you are going to require within the time step delta t. Well, remember now delta t max is smaller than delta t, so this number will be greater than 1. So at the very least, you'll be breaking the time level up into 2 sublevels, where each time step subinterval is now, so your new time step of the subinterval, delta ts, is equal to the delta t that you originally used divided by ns. Okay, and obviously you're going to have to do this as an integer division, right? Because you don't want this to be a real number. So delta t over delta t max is not necessarily an integer, so you're going to have to do a rounding there. But this is essentially what you're going to do. You're going to break up into ns time levels within that time step, and every little sub-interval time step size is going to be delta t divided by ns. Perform these validation at every time step. Every time you loop the solution to a new time level, you're going to perform this validation. And that should work. That makes the algorithm significantly more complex in a sense. Obviously, you have more lines in the algorithm. You have the loop. You have a loop within the loop. And then now you have a conditional, because you have to ask a question. Is this number greater than this one? And so on and so forth. But it really doesn't do much to it in terms of computing time. Okay, you're essentially performing the same number of iterations. You might actually have to break up into smaller pieces, but you don't have to break up into smaller pieces for the entire time domain. You have to only do it for the time level where you need it, and that will significantly accelerate the solution for when you expect the solution to be not necessarily nicely behaved. Okay, so let's test this. We're going to test this with an initial value problem whose equation is nonlinear. Okay, and remember, nonlinear equations usually are expected to behave strangely, not necessarily singular, but maybe yield 2 solutions, non-unique solutions, or more. So I'm going to test this method using the RungeKutta 4, let's just call it 4, because we formulated the 4th order of RungeKutta. There's RungeKutta that are higher order than 4, but we're going to use a RungeKutta 4 scheme for the following initial value problem. So we have a governing equation that is first order in time, such that this function y of t is minus 5 t to the 4 y squared. So as you can see, this equation is nonlinear because you have the y to the power of 2. That makes it nonlinear automatic. And with an initial condition, y0 is equal to 1. So at time equals 0, the solution is equal to 1. By the way, and I'm going to write it here as a note, the exact solution to this initial value problem is I solved it already. Y of t is equal to 1 divided by t to the 5 plus 1. I believe we already did this in class. This is a case that happens to be separable, okay? Because you can leave the t's on one side and the y's on the other, then integrate this whole thing, and you get this exact solution. And at time equals 0, as you can see, you get y equal. You replace time with 0, you get y equal 1. So it satisfies the initial condition. You can plug it in here, and you'll notice that it also satisfies the governing equation. So this is a linear solution to a nonlinear equation. All right. Now we're going to, for the purpose of this demonstration, we're going to let the final time equal 3. So we are interested in knowing the solution from time equals 0 to time equals 3. That's some physical time that has some physical meaning. And we're going to let n be equal to 10. This is not the order of approximation. This is the number of time steps. This is an unfortunate choice of variable names that I didn't notice, but n we've been using as a number of time steps. So we're only going to break up the time domain into 10 time steps, so 11 time levels. Each time step is a size 0.3 seconds or years or whatever these time value or time units are. Experiment with different values of the tolerance epsilon, such that go from 10 to the minus 1 all the way to 10 to the minus 6 and see what happens. Okay, establish that the tolerance that you arbitrarily set, I don't want my solution to be, if you use 10 to the minus 6, you're basically saying, I want my solution to be at least accurate to a bound of 10 to the minus 6, within an order of magnitude, not order of magnitude, actually within the bound of 10 to the minus 6 in the absolute error. All right. So, and then implement this. Well, you need to implement it to be able to play with the tolerance. Implement in MathCAD or MATLAB or any other programming language of your choice. You're free to write your solution to your algorithms, translate the ones that I provide for you. But that's the idea. All right. So let's see what happens. Again, this is a very simple scheme that significantly complicates the algorithm in a sense, because you're adding lines and conditionals and so on, but it solves a problem for you, because notice I'm going to test this with an n equal 10 and you'll see that the solution that you provide that it yields is actually very good. So adaptive time stepping, this is the MathCAD file. I'll post this on Canvas for your usage, and the function that defines the governing equation is minus 5 times t to the 4 times y squared. Again, this is definition equal, and the initial condition y naught is 1. Again, this is not an index, it's just a subscript. I used the dot for a subscript, just for visualization purposes. It's not y bracket 0. The exact solution of this differential equation is given by this function that we just wrote in here. We're interested in knowing and approximating the solution between time equals 0 to a final time of 3. We want to break the time level into 10 steps, or the time domain into 10 steps, and therefore the size of the time step, which is tf divided by n, is 0.3. Very coarse time stepping. Okay. If you try to do this with Euler without adaptive time stepping, the solution will actually be all over the place. You'll have a very, very large error if you use this DeltaT size. Even with Hoynes or modified Euler, you'll get a very large error out of these. So what I'm going to do first is create an array ye, which has the elements of the exact solution. So I'm going to take the exact solution, evaluate it at an array of time values tn. This is an index n, so this is t left bracket n is n times delta t, which yields a t array of 11 values from 0 to 10, 0, 0.3, 0.6, and so on and so forth. And it's using this range variable n that is defined as a variable that goes from 0 to n. If I evaluate the solution at time equal 1, I get 0.5. I don't know why I did this, but I can delete this. It's not necessary. This is just a way of evaluating this function. So then I plot this function by inserting a graphic and playing with the formatting of that graphic to show the grid lines and the trace and so on. And this is what I get. This is what this function looks like. And notice this is very coarse because I use a very coarse value of delta t. If I were to say, well, I want 100 time steps in between, the solution will look a lot smoother, but the values won't change. All right, so I just want a coarse approximation for illustration purposes to demonstrate that these approximation methods can do a good job when we use adaptive time stepping. Again, it makes no sense to use an approximation technique when we know the exact solution. If you know the exact solution, what would you approximate it? But the whole purpose of these is to test whether these approximate solutions are accurate and to what degree. So let's start with a tolerance value of 10 to the minus 1. This is the tolerance, or what we call epsilon, in the notes. So the RungeKutta 4 algorithm. This is the programming algorithm. First of all, the first element of y. This is the first line. The first element of y. This is indeed an index. All right. This is left y left bracket 0. This is the 0th element of y is equal to y naught, which is a given initial condition. So we're assuming that we know the solution. It's not an assumption. We know the solution at the first time level. That's y naught. Now we're going to loop from n from 0 to n minus 1 to the total number of time steps. So basically from 0 to 9, so that we can approximate the values at the next time level. Now within this loop, we are going to approximate the solution twice. We're going to get two estimates of the solution at the same time level. One we're going to call y1, which is using RungeKutta, the predictor and the tree correctors for RungeKutta, using a full time step. So I get y1. This is y1 is the approximation at the next time level using a single time step. Then I'm going to break up the time step in two. I'm going to say delta t2 is delta t divided by 2. And what I'm going to do is I am going to perform a loop inside of these to get a new estimate of the solution from 0 to 1. So I'm going to go half a time step and another half a time step in order to get to the solution y2. So I calculate the predictors k1 through k4 and correctors k2 through k4 using the new value of delta t, which is delta t2, which is half of the original delta t. And then I'm going to do this twice, so basically two steps, two half steps. Then I have y2. All right. So y2 and y1 are my two estimates of the solution. I expect y2 to be slightly better than y1 because this one was estimated using smaller time steps by a factor of 2. The error in the approximation is 16 over 15 y2 minus y1, as defined by the formulation that we derived. So the next estimate of the solution, yn plus 1, is equal to the previous the solution of the previous time step y1, the one we call y1 originally here, plus the error. All right, so this is the best approximation that I can get at the next time level using two estimates of the solution. Right? Now I'm going to see if the error between these two solutions, these two estimates, satisfies the tolerance. All right, so basically, if the error that I calculated is less than the tolerance, so the error is, if the error is less than the tolerance, then the error is equal to the tolerance. And what I'm going to do here is say, well, delta T max, the maximum value of the time step that I have to use to be able to achieve the tolerance that I prescribe, is equal to delta T times tolerance divided by the error to the power of 1/5. So if delta t over delta t max is greater than 2, so that means that delta t is larger than delta t max by at least a factor of 2, that means I'm going to have to break up the delta T into sublevels NS. And what I'm going to do is I'm going to take the floor of delta T over delta T max. The floor is just rounding down, plus 1. And this new size of the time step for the sublevel iteration is going to be delta T divided by NS. And what I'm going to do is I'm going to loop NS between 0 and NS minus 1. So I'm looping over NS sublevels or sub-iterations within the time step, calculating the predictor and the tree correctors for that new delta TS, and calculated the new estimate of the solution. At the end of this loop, I have a new estimate of the solution. Yn plus 1 is equal to Ys. So if the error was not satisfied, the tolerance was not satisfied, it goes into this loop and it calculates this estimate. If it was satisfied, I already have an estimate that I call Yn plus 1. And then this loop is repeated n number of times. This goes back to the original loop, n number of times, because I need to estimate the solution at every time step. And the subdivision, or the sublevel iteration, or the time adaptation is going to be performed only when it's necessary, only when the tolerance is not met. At the end of this process, I get this answer, which qualitatively looks fine, even though it only has 11 points, 11 discrete solution points. It seems to approximate the analytical solution, the exact solution, very well. In fact, if I calculate a residual between the exact and the RungeKutta solution, I get 0.011%. So it's a pretty good numerical approximation. However, it might not be enough for what we need. So what we do is we go back and say, well, let's make the tolerance now 10 to the minus 2. And if we make the tolerance now 10 to the minus 2, what is the new error? Well, the solution still qualitatively looks good, and quantitatively looks exactly the same. Nothing has changed. So increasing or decreasing the tolerance by a factor of 10 doesn't do much for the solution. That is an indication that there's no adaptation needed in the entire solution process under this tolerance. If I make it 10 to the minus 3, and I go down, update, same thing. So the fact that I'm getting the exact same error in the solution, the exact same residual between the exact and the numerical solution, is an indication that there was no adaptation in the first place. Under this tolerance, there's not one particular time level where adaptation was required. And you can see that the solution is very smooth. The exact solution looks very smooth, though it's very rare in this particular case that an adaptation will be performed. If we decrease the tolerance to 10 to the minus 4, qualitatively the solution looks to be good, but now there's a slight difference in the residual. That means that at least in one of the time steps there was an adaptation being made. It broke the solution into at least 2 or 3 parts. If I make it 10 to the minus 5, let me update this. Now we're going down, the residual is going down to 3.329 times 10 to the minus 3%. Means that qualitatively, again, you cannot distinguish the two solutions, but now quantitatively, this is saying that the new solution, YRK4, is much better than before. Before it was 1 times 10 to the minus 2%, now it's 3 times 10 to the minus 3%. And I can keep on decreasing this tolerance level, and you will notice, if I update this, F9, now I'm at 10 to the minus 4, so that residual keeps decreasing. Again, I am not doing anything to the problem. I am not breaking it up into smaller time steps. The original time steps still very coarse, but in some of these instances, maybe when the slope is really high, the method actually notices that it needs to break up into smaller time values and time steps to be able to satisfy that tolerance, and it does so, and it produces much better results at these 11 locations. It's not calculating the residual at any other locations other than the 11 original locations where the time steps are located. And maybe right here where the solution seems to settle down, when the exact solution seems to settle down, the algorithm determines that it doesn't need to perform any time stepping, and just leaves it at the high value of 0.3, which is the original time step. So this is it for today. I just wanted to give you these this technique. We're going to show you this technique to efficiently and effectively break up the time when needed only. That's what makes it efficient, so that we don't have to use a very small time step for the entire solution process. Only the algorithm will determine intelligently when it needs it, and then it will perform the adaptation itself, and yielding a very small error, as you can see. So this is all I wanted to go over today, and again, thank you for your attention, and I'll see you in class or in the next video. Goodbye.